差不多，他们开车已经开过去了，准备可以叫一些志愿者去帮忙。他们已经把东西运到下面了。去帮忙就是把东西拿到那边去。
那你要跟他们讲，你现在要主持这个。
Are we starting?
Yeah, because our classes.
Yes.
Yeah, okay, great. Great.
Good afternoon, everybody. Very happy to have you all here for our Pi Day keynote speaker event. We are very, very happy to invite Professor Daphne Liu from Cal State LA to come here to share with us her wonderful experience. She was the recipient of the Presidential Distinguished Award for 2018 of Cal State LA. She was also received the Distinguished Teaching Award from the Mathematical Association of America in 2015. And she's the PI, which is the Principal Investigator for National Science Foundation. I cannot have enough time to name all the rest. So let's give her a round of applause to give us the day's speech. It's going to be on beauty and power in mathematics.
Thank you, Professor Zhang, for her very nice introduction. It's my great honor to be here to meet you and to share my experience with you. Secondly, today, indeed, this is my third year I participated in this Pi Day event. I really enjoyed it very much. Especially today, I participated in this panel, career panel, hearing 6 inspirational stories from our panelists. It's great. It's a wonderful experience. And I think the third one is I want to congratulate students here at PCC. I think you have a very dedicated faculty and who really care about your learning and spend so much effort and work to put together this event. I cannot imagine how much work they put together. I still got the text from Professor Zhang last night at 12 midnight about all the details today. I said, well, you should go to rest. So it's really, I think you're really fortunate to have a dedicated faculty and who put up this platform. I think this is a very friendly platform for people to share math or related to math, STEM, to share achievement and to hear achievement, to make connection. So I really congratulate you. So today, I would like to share with you my experience about mathematics, my journey in mathematics, some stories with my students. Yeah, okay. I think we all know math is practical and useful, right? Okay, and today I will also show you that math is also beautiful, and I will share with you why I think it's beautiful and powerful. First, let's start with math is practical. Well, what do we mean practical? After you graduate from PCC, you graduate from college or get to a graduate degree, what's the eventual goal you want to have? Right, job, right? Yeah, job. That's very practical, right? Thank you very much. That's job. Okay, how you find the best jobs? How do you find your jobs? What do you define what are the best jobs? Well, best jobs of the year. There's careercast.com. They do this survey every year. they're based on four criteria. What do you think when you want to find a job? What's the most important thing? First one is what? Income. I heard from one of the panelists today, money is the most important thing for a job. True, right? We want to survive. Second one is growth outlook. So how much growth outlook this job will bring you, or you're just doing the same thing every day, one day after another. The third criteria is work environment. You want to work at a very friendly environment. So work environment is also very important. And the last one, fourth one, is stress level. You don't want to be at a job that is very stressful, right? So based on these four criteria, this careercatch.com in the past, I think probably 50 years already, every year they did this survey about hundreds of jobs. And this is their result. This is the result from the past 5 years. The top 10 jobs, they have the best 10 jobs. Also, they have the worst 10 jobs. I encourage you to look at their website. These are the top 10 jobs in the past 5 years. Okay, you can see that mathematicians are ranked very good. Especially 2014, we are top 1. And 2018, last year, we are the second. Followed by university professor. I think I have the best job in the world. So if you look at today, I also heard from the panelists that statistics is very, very useful. So you can see statistician, which is the closest to mathematics. You can see statisticians ranked among the top 5 in the past 5 years. Yeah, so especially 2017, statistician is the top 1. If you just look at more, actuary is a career based on probability and statistics, which ranked very good too. If you look at even more, like data scientist, operations research, software engineer, computer system analysis, these are all the jobs that are related to mathematics. And they use a lot of mathematics. So from this table, the conclusion is, if someone is good, he or she is good in mathematics, then he or she has a good opportunity to get one of the top 10 jobs. So that's why I think math is very practical. So especially, I think, at PCC or community college, you have dedicated faculty. Mathematics is a very important foundation for probably all the highlighted jobs here. So listen to your professors. Secondly, I want to say that math is useful. Of course, we know math is useful. We use math everywhere. I want to give you an example that you're using every day. Google Maps. Do you use Google Maps every day? I use every day, almost every day, maybe more than once, multiple times. You know, Google Maps, especially when you want to go from one location to another, from location A to location B. For instance, this one, I think, is from Pasadena to Area X. Before you go home, before you leave, you look at Google Maps to find out the fastest route, right? To go from location A to location B. Why this is math? Oh, I'm a graph theorist, and this one is, we can use a graph theory to model this question. Indeed, this is using graph theory as a model. This is a graph model for this Google map. You use a vertex to represent a location, and the number next to the line represents the distance or time, depending on you want to find a shortest route or fastest route. And there's a popular algorithm in graph theory called shortest path algorithm, which you just input the algorithm, you just code the algorithm, you can find the shortest route from any location to another, especially because of the advances of technology. Right now, we can do very fast. Okay. So graph theory is my specialty that has a lot of application in the real world. Let me name you another one. Another one is after I introduce the beginning of a graph theory. Graph theory started from 300 years ago in 1736, around 1730s. There were 7 bridges in Königsberg, right now in Russia. In this small town called Königsberg, there were 7 bridges. Oh, sorry, I hit the. Wow, so you see all my secret now. So the Königsberg, there are 7 bridges. There are 7 bridges, right? Okay, connecting these islands. This was 300 years ago. There was no TV. There was no computer. There was no computer game. So at that time, people had to create games by themselves to entertain themselves. So they asked this question: is it possible we start from one location, one of the land, and then cross each bridge exactly once, and land at the same place? Is it possible? Okay, I don't know who created this game, but they got very interested into this game. They ran, they walked, they jogged, they got a lot of exercise. For many, many days, for months. They couldn't find the answer. They tried, and tried. They couldn't find a route, starting from the same location, starting from one location, any place, and end at the same location, but crossing each bridge exactly once. They tried very hard, but they couldn't find the answer. So until Euler, driven by curiosity, Euler wanted to find out the answer. Okay, so he created the very first graph model, which is this one. He represents each location by a vertex, a round vertex, and representing each bridge connecting 2 locations by a line. Okay. So instead of running a lot, he just looked at this model, this graph model. Okay. Can you hear me? So you can see from the graph model, if you start from A, for instance, okay? Now you think about, can you start from A and end at A by crossing each bridge exactly once? So if you start from A, you choose one of the 5 bridges, right? Connecting to A. You choose one of them, no matter which one you choose, maybe the second one. Then remember, you have to cross each bridge exactly once. Wonderful. Thank you. Exactly once. So no matter what, you're going to use another second bridge going back to A. Right? One bridge out from A, one bridge into A, and then one out, one in. And how many bridges are here? 5. 5 is an odd number. The first one is out, second one in, third one out, fourth one in, and the 5th one is what? Out. So you never be able to come back to location A. By looking at A itself, by looking at these 5 bridges without looking at other bridges, just looking at the location A, it's impossible to. Okay. Oh, thank you. So just from A, you can see it's impossible. Same thing. Why? Because 5 is an odd number, right? 5 is an odd number. 1 out, 1 in. Odd number always out, even number in. So the last one is the 5th one, which is odd number going out. You never be able to come back to A. Same thing for if you start from location B. B has how many bridges incident adjacent to it? 3. 3 is an odd number or even number? Odd number, right? So again, from B, if you go one bridge out, one in, and the third one is out, you never be able to start from B and end at B. Similarly for D, again, it's 3, right? 3 edges out from connecting to D, and the 3 edges connecting to C. So they are all odd numbers, so it's impossible. So the answer is no. And this is the proof to show why there's no. Instead of running a lot to show people it's impossible, we use a graph model. So that's the beginning, the very first graph model of graph theory. Since then, graph theory has become one of the branches in mathematics, like algebra, geometry, number theory, topology. And I think in the past probably 30 years, graph theory has been one of the fastest growing fields in mathematics. I think statistics is also, that's partly because of its a lot of application, real world application, and the second reason is the advances of technology. Okay, so now I promise you to show you another application. There are so many applications in transportation, in scheduling. This example is about job assignment problem. So for instance, if you have a number of jobs, A, B, C, D, you have 4 jobs. And you have how many candidates? 7 candidates. So you have this diagram. You put all jobs on one side and all candidates on one side. And you're connecting one job with one candidate, meaning that candidate can do that job. So if you're a manager, how you assign jobs to these candidates, right? That's a very good question, possible. And so this is, again, a famous topic in graph theory called matching theory. You want to find the maximum matching. You want to find the best matching, the best result. Again, there's an algorithm about this. If you look at, this can also be law of connection. This application is so-called law of connection because you can have all boys on one side, all girls on the other side, making a connection about that boy and that girl. They are willing to have a dance or something. That can be a law of connection. If you Google MIT, I think the MIT computer science graph theory, there's a lecture by MIT professor which really talks about law of connection, which is also very, very hilarious. I recommend you to look at that one. So this is just another example I show you. There are many other examples. So the next, I would like to show you that math is beautiful. Why math is beautiful? Beauty comes from curiosity. As this Abraham Flexner, this is a very classic essay published in 1939. The title of the essay is The Usefulness of Useless Knowledge. He said that throughout the whole history of science, most of the really great discoveries, which had ultimately proved to be beneficial to mankind, had been made by men and women who were driven not by the desire to be useful, but merely by the desire to satisfy their curiosity. I encourage you to Google Flexner. Flexner is the founding father for the Princeton Institute of Advanced Mathematics, which Einstein was there. He's the founding father. He also, there's a video produced by Princeton University in 2017. I encourage you to look at that video, only 4 minutes. Director of the Institute of Advanced Mathematics. He was the speaker for that video. He mentioned about Flexner's vision at that time. At that time, there was no internet, but he has a great vision, not just in mathematics, but also in medicine, in chemistry, in physics, in many things. This is a short article, so you can probably only 3 pages, but it's very classical. So I encourage you, if you're interested, you can look at this. Okay, so I'd like to share with you my math journey. First of all, I'm a first generation. I know some of you are first generation. I'm a first generation. My parents were refugees from China Revolution in 1949. They escaped to Taiwan, where I was born. I was born in Taiwan, and their education, my mom was only 9 years old, but my father's education was interrupted. So I know I grew up with, education is so important. So my journey about mathematics is, I started indeed with an aha moment. When I was in junior high, I was sick at home for a few days. I had to study the math lecture by myself, and there were a lot of trigonometry formulas and equations, and they didn't really make much sense to me. And I tried, so I tried to derive those formulas. So eventually, I was able to derive those formulas, and I got so happy. Everything made so much sense after that. And I feel like, and right now, I still have that habit. That is, when I see a formula or a theorem, I like to know the story behind. I really like to know why we have this and why the formula is that way. So I keep that habit. And I enjoy that very much. So I went to college. At college, I took a graph theory course, which changed the course of my life. I think that's why I got my PhD. I found graph theory so visual. Everything is, I was very curious indeed. And the professor just got his PhD and his postdoc from US to Taiwan. That was his first year. So I witnessed that he's so busy doing research. I was curious, what is research? I asked him, but of course he was not able to answer me, so I thought I'm going to find out myself. So I also took other classes from the same professor, who's a great mentor of mine. I was very fortunate. We did a joint paper still lately. He's a great mentor. So because I was very curious, that really started my curiosity about research. So I entered Academia Sinica, which is the highest research institution in Taiwan. I was very fortunate that I was recruited there. I spent 2 years, and I got 2 years of very rigorous training in research. That's very hard, just from a student just got BS degree. But it was so hard, almost cried every day. You probably don't believe me. It's very serious like that. But afterwards, I feel like I like it. I like to do research. It's like you find out something people don't know the answer. Of course, you learn the method. It's very hard because you really need to prepare yourself. You need to look at what other people, what have been done already. That's very tough. But once you go through that, I feel like, I like to learn more. So I decided to get a PhD. At that time, I wanted to be a researcher in graph theory. I really wanted to just do research every day. So I went to US. That's my first time I took a flight. That's my flight to US. That's my first time in my life. So that was very exciting. I was very excited. So I took, the college. So I came for a PhD. I didn't go to a very famous PhD program. I know some people might think you must go to a very famous one, but I think it really depends on how much you learned in your PhD and how much you study, you work after your PhD. Doesn't matter, you really need to go to a very good brand. Indeed, I learned so much. I also got a mission from other university, but I went to University of South Carolina, Columbia. Because they gave me full scholarship, and I really appreciate they trust me without seeing me. I was in another country, right? Totally, never seen me. And I learned so much, and I had a great mentor from that university, and that really So I think really doesn't really you have to go to a very famous one or not. It really depends on how much you like it, how much you learn, how much you use what you learned. Okay. So after PhD, I was very fortunate. When I was a PhD, I was a TA, and I found my passion for teaching. It really inspired me because I saw students. When I was in Taiwan, I don't know, you probably don't know Taiwan and Chinese culture. When we were sitting in the lecture, we just sit there just like a stone. We don't ask questions, we just copy all the notes. But probably right now it's different, but 30 years ago, culture was that. But so when I came to America, when I was a TA, I was very inspired by my students because I can really see they understood what I said from their faces and from their eyes, and that their eyes open wide and their faces just light up. I feel like, oh, I really like that. That's my passion. So I found my second passion. I think I have two passions. So I decided to have a scholar and teaching career. So very fortunately, I joined Color Theorem and did it that year. I think there were like 300 people applying for that one position. So I was very fortunate. I was coming from, that university far away, not from this West Coast, right? So I think I'm very fortunate. When I interviewed Color Theorem, that was my first time to come to Color Theorem, to come to Los Angeles. So a lot of adventure in my life that. So after PhD, so I joined Color Theorem and I created a graph theory class because I wanted to inspire my students just like my mentors inspired me. So I recruited some students from my graph theory class if they really wanted to do research. So that's my story. Okay, so that's my story. And after my story, I want to tell you that not everyone discovered the beauty of math at the same time in their life. Some people are earlier, some people are later. Doesn't matter, even though for mathematician, can be early, can be later. I'm going to show you a few stories. Indeed, I have so many stories from my students, but I'm just going to show you few stories. I have some students sitting in the audience. Okay, just show you a few students' story. William Hua. He entered Color Theorem when he was 12 years old. We have this early entrance program. And he was originally majoring in biology, like his parents wanted him to be a doctor. He was majoring in biology. But he took a probability, I think, with me, and then later on he decided he wanted to do math. So he loved math, applied math. And he took a graph theory class with me and did a research project with me, and he entered Johns Hopkins University. Right now he's still there. He's applied math and statistics program. He was the youngest of Color Theorem 2015. He got his BS degree. And second one is Sam Chow. Sam is a very special person. He has I think he's the deepest passion in teaching mathematics that I have ever seen. Okay, he gave up UC Berkeley pre-med admission and came to our campus, undergraduate mathematics, because he wanted to be a math teacher. He's really amazing, and he took probably 7 classes with me, and he graduated 2 years ago with a master's degree. And writing a thesis with me. During his years, undergraduate and graduate career in our department, he got every exam 100%. No exception. Every exam, every subject. He worked so hard, and he's so passionate. I still remember when I teach maybe probability or modern algebra, his eyes, he always sat in the front row in the middle, his eyes just grow, glow. I still remember that when he hears something amazing. Yeah, okay, that's Sam. The next 2 students, they come from related but not math background. Okay, Sarah Jamsidi, she was a graduate student in math but double major in economics. I think her background in undergraduate degree is economics. And she was double major math and economics for a graduate degree. She took my graduate level graph theory class, and she created a coloring game and did a wonderful presentation. And then he went to Penn State for a PhD, and right now he's a postdoc at the Illinois Institute of Technology. Ms. Kobayashi, do you know him? If you are from Cal Poly Pomona, he's now teaching at Cal Poly Pomona. Ms. Kobayashi worked at the City of Hope for a few years. After he got a BS degree in chemistry from Caltech, he worked at City of Hope for a few years with a chemistry degree. One day, I think his passion for math was calling him, and he decided to come to our graduate program to take classes. And the first class he wanted to take was graph theory, and later on he worked with me for 1 or 2 years under my first National Science Foundation research grant. And then he went to Dartmouth College for PhD. Right now he's a faculty at Cal Poly Pomona with a chemistry degree. Okay, the last 2 students I want to show you are even more remarkable. They come from humanity background. Humanity background, yeah. So Grant Robinson, Grant Robinson got his BA degree from in Latin and Greek. Latin and Greek. Okay. And he worked for a couple years for different jobs after his graduation from UCLA. He took one class at PCC. He thought he wanted to try his math ability. He took a calculus class. He told me that kind of really challenged him in the beginning. He got a D in the first quiz, and then he worked so hard. Eventually, he got an A. So he also appreciates faculty from PCC, which really inspired him. And then after that, he came to our master's program. He worked with me a few years, funded by NASA and the National Science Foundation. He likes to share mathematics with others. This is it. Do you know this one? Does this one look familiar to you? Do you know what he's wearing? A t-shirt, right? This was 2 years ago, Pi Day. That's the t-shirt 2 years ago. He was showing his poster to students. Yeah, he participated Pi Day in the past 3 years, and he really enjoyed it. Yeah, so this is a great event to inspire my students too. And the last one, Colleen Bloomfield. Do you know what his degree in undergraduate degree majored in? Fine art. He was majoring in fine art, painting, oil painting, TV producer, film producer. He worked a few years, and then after his degree. And then I think one time he was thinking about math is really cool, and he started to learn by himself. After that, he was not very satisfied, so he went to community college. I think it's probably both PCC and ELAC. He took a few classes there, and eventually he came to our master's program, and he did very well. Indeed, both Grant Robinson and Colleen, they are our outstanding graduate students of the year. They were outstanding. They did very well, and Colleen right now, Colleen and Grant Robinson, they both entered a PhD program last fall, 2018. And Colleen is in Vanderbilt University. Beside Colleen is Jeanette. Jeanette right now is his wife. They were just in my research group at that time. They just got married in December. Jeanette is now working on her master thesis with me. So with different backgrounds, it's possible that sometime your passion for math will be calling you. So I think every student has potential to do well in math, just like the back of my t-shirt. Do you know what the back of the t-shirt says? I can do math and you can. I almost want to wear it to the other side. Okay, the back side said, I can do math and you can. I think every student has potential to do well in math. My job is to, of course, teach content also to inspire students' curiosity in mathematics, because curiosity will motivate their study. You study, and then you find a result. Two methods I find to engage, good way to engage students is, the first one is to relate math to something related to their daily life, something easy to remember. Like this one, do you know what is this one? Does this one look familiar to you? This is in a calculus class, right? This is in a calculus class. You try to find the volume. I showed my secret already. This is in a calculus class. You're trying to find the volume of this object. What you do is you cut the volume and the object into slice them to very thin slices, right? And then stack them together. That's called integration. I call integration continuous summation, because summation is this, right? Integration is when you write summation very smoothly, very quickly, you get integration. Integration is continuous summation. So when we summate, when I introduce this, when we need to cut the slice into very thin and round, I tell students, we are stacking pancakes together. Different sizes, from smaller size to larger size, just like this, because they are very thin. The shape is very thin and round, so I relate that as pancakes. And if you see the next one, this one, again, we want to find the volume of this object, and we slice them into small, very thin pieces, and each piece is a rectangle. So I call this one, what should I call this one? Waffle. Yeah, I call this one waffle. I say, well, we stack waffles, different sizes, vertically together and press them together. Then we get a volume. Okay, now if the next one, what do you think about this one? Donuts, right? Yeah, exactly. Yeah, this is the one. So I call this one donut. We stack donuts together. Textbook says washer. So you ask me, what is a washer? I say, well, let's use donut. So students from my calculus class tell me that they feel hungry after my class. They line up at a cafe. They say, wow, they complain, why we don't have waffles, you know? So they kind of complain that I made a long line for the cafe, but you know what's my main purpose? Do you know what's my main purpose? My purpose is when students are eating a donut or a waffle, next time they think about integration. I wish they do that. Okay, that's my purpose. So I like to relate things to something that they can easily remember. Okay, so the next method I think effective, I like to relate students is I tell a story behind a formula, like a storyteller. Do you know every math formula? Do you know every math formula tells a story? Every math formula has its own story. Okay. So here I'm going to share few stories with you. Some stories are short, some are poems, some are games, and some are novels. I'm going to give you an example for each one. First, start with a short story. A short story of math, a formula is this one. Okay. Have you seen this formula before? Okay, this is an addition of odd numbers. Okay, the first line, we begin with the number 1, first odd number, right? The second one is we add 1 and 3 together. We get a 4, which is square of 2. And then 1 plus 3 plus 5 is square of 3. 1 plus 3 plus 5 plus 7 is square of 4. And then up to 9 is 5 square, 6 square, together, we can write this equation and use sigma notation, I from 1 to n. We add 2i minus 1 together, I from 1 to n. The outcome is n squared. This is the formula. Formula usually look very scary, right? This formula, why this formula? Why are numbers and squares are related to each other? What's the story behind this formula? Okay, I'm going to show you the story behind this formula just by using a diagram. Okay, let's start with why. Let's start with the number 1 token, right? We have 1 token. And then we add 3, 1 plus 3, we add 3 tokens here on the side of 1. So we have 4 tokens. 4 tokens is 2 by 2 square. Okay. Now what we add the next odd number? After 3 is what? 5, right? 5? Is that 5? Sure? Okay, 5. Okay, where should I put the 5? I put the 5 on the side again of these 4 coins. I put this 5 here. This 1, 5 is 2 times 2 plus 1. So these 5 tokens together, I make a 3 by 3 square. Our numbers adding together become a square, right? What is the next one? 7, right? How we put that? Where should we put the 7? Yeah, all right? Just again, I encompass this, it's a 7. Why this is 7? 3. I have 2, 3, right? 2 times 3 plus 1 is 7. So adding 7 together, I have a 4 by 4 square, which is 16. So you can see this pattern goes on and on. So I don't need to really remember that formula. This is the story behind that formula. Just draw this diagram. And this is the story for this, equation, formula. It's shorter story. The next one I'd like to show you is a poem. Math can be a poem. Have you heard a poem of math? Okay, so this one is, I named this one a poem. Of course, it's not a poem. Why I think this one is a poem? This is infinite geometric series. 1/4 plus square of a quarter plus third power of a quarter plus all the powers of quarter. I have infinitely numbers adding together. This is infinite geometric series, right? Have you heard about this before? Infinite geometric series? In algebra class, right? In pre-calculus class, this is called infinite geometric series. Why I call this one a poem? Because the rhythm is a quarter. You see, every term has a quarter. This is a quarter, square of quarter, third of quarter, fourth power of a quarter, so on and so on. So this is infinite poem. Okay. So what is the sum of this? If you remember, do you remember the infinite geometric series formula? The common ratio is 1/4, right? Common ratio is 1/4. So it's 1/4, the first term divided by 1 minus a quarter. Come out with 1/3. If you simplify, the answer is 1/3. Okay. Why it is 1/3? If you forgot infinite geometric formula, it's okay. I'm going to show you the reason behind this. First, we start with an equilateral triangle. Equilateral triangle of area 1. Right? Equilateral triangle of area 1. And then we divide this triangle into 4 triangles. 4 triangles, and we shade the middle one, blue. Now, what is the area of this blue triangle? 1/4, right? Because the total triangle is 1, so this is 1/4. And the next one, I want to add a square of a quarter. What I do is I do the same thing to the top triangle. I divide by 4, so shade the middle one, which is square of a quarter. And then this one is the third power of a quarter. And infinitely, you add infinitely many triangles together. Do you get it? The first one is a quarter blue, right? And the second blue one is the square of a quarter. The third one is the third power of a quarter. If you add all these together, what is the total? Why is 1/3? Yeah, you know it's 1/3, right? How can you show 1/3 from here? I just shade this triangle into 3 colors. Okay, you see green, blue, and yellow. Right, green, blue, yellow. On the first row here, you see green, blue, yellow, so each one is the same size. And then the second row here, again, green, blue, yellow. Green, blue, yellow, green, blue, yellow. So you can see the 3 colors of these triangles divide the whole triangles into third, and third. So without using the infinite geometric series formula, we can come up with the answer 1/3 without the formula. Without knowing the formula, it's possible. So this is the story behind this formula, which is, I think, interesting. Yeah, okay, so now let's look at what's next. Oh, yeah. Can you find out, can we replace 1/4 by 1/5? 1/5 plus 1/5 square plus up to this is 1/4, and the next one is 1/6. Replace 1/4 by 1/6, and or in general is the most general one is this one, 1n plus 1n squared plus this. Yeah, I will offer some prizes to you if you can find the answer for the student who can find, or student or teacher. The first one who give me the right answer, I will give you a small prize. Okay, but not right now, okay, after the talk. So think about what kind of shape we can use. For 1/4, we use triangle. For 1/5, what we can use to show this infinite geometric series without using formula, but using diagram. Okay. So, next one I want to show you is, as I promised, it can be a game. So we're going to play this game very quickly. First game is, I know they printed out something. Professor Zheng, the printout. You want to give to them? So first one is, first game is, we just start with 1 and 2. Okay, it's okay. I just show you because I have it. So 1 and 2. And then you divide this 1 and 2 into many small segments by using these dots, right? By using these dots. And then on these dots, you can use any label, 1 or 2, on the dots. This is just one example. Okay, so you start with 1, 2 line segment, and you put dots in between this 1 and 2. You can put as many as you want. Okay, and then you label each dot by 1 or 2. Yeah, it's one side, not the triangle side. Yeah, triangle is the next one. On one side, there are 2 sides. On the flip side, yeah, they are 2-sided. So one side has this 1, 2, right? 1, 2. I encourage you, every one of you, the first step, you don't have to do anything. The second step, there are empty dots, right? Put either 1 or 2. On each dot, put 1 or 2. If you don't have a pencil, just grab one from your neighbor. No, just see if someone can lend you. Okay, just put anything 1 or 2 on those bubbles. 1 or 2 on each bubble. There are 4 bubbles, right? 1 or 2. Each one is 1 or 2. Yeah. Each bubble is 1 or 2. Yeah, you can do that. Yes, each bubble, the step 2. Just look at step 2. Each bubble is 1 or 2. If you are done, please raise your hand. 1 or 2, not the triangle. Look at 1 or 2. Yeah, you're done. You raise your hand. Thank you. Okay, thank you. Okay, so the next one, step 3. Use 1 or 2. Yeah, it's okay. Step 3 is I want you to find out how many 1, 2 segment. How many segment is 1, 2? Like this one. This is my example. Right, this example here. I have how many 1, 2 segment? I have 1, right? 1 here, right? 1, 2. And this is another one. This is 1, right? How many 1, 2 segments? 3. For you, it might be different. Everyone has a different answer. How many 1-2 segment? 3, okay. 5, okay, good. Dr. Bloomfield, how many? 5, 2, 3. 3, he has 3. You? 3, okay. Ming? 3, okay, 3, 4. Anyone has 5? 5, and good. Anyone has 1? Good. Anyone has 3? Anyone got 2? You have 2? Can you double check his answer, please? How many? Okay, good. 1, 2, 3. He has 3. Yeah, he forgot 1. Yeah, 3. How many? 3. Okay. How many? 3. Okay, good. How many got a 4? Anyone got a 4? No. Okay, good. So, so indeed, what you are doing is a special case of a very famous film called Ashburner Lemma. Out of battery. I think this one is out of battery. Continue. Okay, look at the backside. Look at backside. Indeed, backside is my next one. Okay, you can count how many 1, 2, 3 triangles. I shaded one already. Please find how many 1, 2, 3 triangles in A and how many in B. Okay, I shade one for each one for you already. You can shade, please shade others. And when I'm trying to find a battery, I think it's out of battery. Yeah, A and B. Huh? Yeah, you count the original one also. Yes, you count the total. Oh, no, only count small triangles. Only count small 1, 2, 3 triangles. Don't make it complicated. Life is already very complicated. Just count small 1, 2, 3 triangles. Not bigger ones. Ah, got it. You can shade just like what I did. You can shade just 1, 2, 3 triangles. Just a small one within the boundary. For each small triangle, you don't have to look at the big triangle. What you are doing is very famous Ashburner Lemma. Examples of Ashburner Lemma, which can be used to prove a 6-point theorem. It's very serious. Ashburner Lemma, yes. So, sorry, because Professor Zhang told me that we need to finish in about 10 minutes. So I'm going to. Right. So thank you for your trying. Let me give you the answer now. What you're doing is a famous Ashburner Lemma. Okay, now this is how many? Always odd number. Always an odd number of 1, 2 segment. Always odd number. It's always odd number. You probably can prove this. Yes, but we're not going to talk about the proof. It's interesting, right? Okay, the Ashburner Lemma, this is a one-dimensional Ashburner Lemma. Two-dimensional Ashburner Lemma is we start with a triangle, as you have seen, right? I drew for you already. You start with a 1, 2, 3 triangle, and we want to triangulation. This is in topology. Topology say we want to triangulation. Triangulation is to make a big triangle to what? Small triangles. Any way you want, but just make sure it's a triangle. Every region is a triangle. And then what you do is you label the vertices on the boundary. Each label is either 1 or 3 on the boundary. So on this one is either 1, this vertex is either 1 or 2. On this boundary is either 3 or 2. But at the center, in the interior vertices, you can label anything you want. Interior 1 vertices, you can label 1, 2, or 3. So you can play this game with your friends. You can create any triangulation and label them. These 2 examples I just created. Okay, so for this example here, how many 1, 2, 3 triangles? How many 1, 2, 3 triangles? This one only has 1. This example only has 1. This is not the example I gave you. The example I gave you was this one. There are 3 triangles. A has 3 triangles, right? Did you find it? A has 3 triangles. And how many in B? Oh, you're so smart. Yes, B has 7 triangles. You made it. I made a very large number. I was worried. So, yeah, 7. The next one is 7. So this is a Ashburner Lemma. In 1928, it's a very famous lemma. Ashburner Lemma can be used to prove a fixed point theorem. Ashburner Lemma works for any dimension. Right now, what we're doing is just dimension 1 and dimension 2. But 3, 4, 5, it all work. This one has 5, just an example. Okay, so now I show you a beautiful math novel. Boissoulan theorem says that for any moment, there exists a pair of antipolar points on the Earth with the same temperature and the same air pressure. This is like a math and a chemistry, right? Math and physics, right? Kind of interesting. Mathematician, we can prove. We prove that during any moment, every single moment, there exists a pair of antipolar points. Antipolar points means what? 2 points on the Earth that are connected by a line through the center of the Earth. Like North Pole and South Pole is one pair. So mathematician Boissoulan theorem guarantees during any moment, there exists a pair of antipolar points on the Earth that have the same air pressure and the same temperature. It's kind of amazing because, well, the point, antipolar point from our point is, you cannot imagine have the same air pressure, right, and the same temperature. We can only imagine our neighborhood. So this is, and the beauty of this Boissoulan theorem is it works for any dimension. This is just one example I show you. It's really amazing. Why I'm related to this one is because it's related to my biggest aha moment. I'm a graph theorist, right? There was one, 2011, I think, there was a breakthrough of a very long conjecture, very famous conjecture, the proof in graph theory, but the proof was by algebraic topology, which is not my research field. But I was on sabbatical leave, so I spent 3 months studying this algebraic topology and immersing myself in this Boissoulan theorem and other amazing, beautiful theorems. I feel like my life was worthy already. I feel like learning those things. My life was worthy. So it's like in the heaven, okay? So immerse myself. So one day, unexpectedly, I found a shorter proof because original proof was very long, very difficult to understand. So I found a shorter proof. And it came out immediately as a joint paper with my mentor from my graph theory. I was visiting him. I was giving lecture in National Taiwan University. And I think it came to me, the short proof, not because I was lucky that day. It was because I was so amazed, so immersed myself in those beautiful things and trying to find out how they use this, how they are related to each other. I think that curiosity is the key there. Okay, so after that, I want to share excitement with my students, but it's really like climbing high mountain, leading my student to climb a high mountain it's very hard, it's difficult because content is, even though it's a shorter proof, it's still very abstract, very difficult. So, so I took the challenge to teach a class on this. And we need but after I wanted to teach this because I want students to see this beautiful thing afterwards, after hard work. I think that's for many mathematics. You have hard work, but then at the end, you see this beautiful thing, right? If it was too easy, you just stay on the same level. You don't see beautiful sceneries, right? So I want my students to see this. So I want to give them good equipment. Equipment means something they can grasp to imagine some abstract concept. So we're making some object related to Boswell film. And the students also check your answer by pairs, and they also share their answers with the class. And we had a good time finding these round things around us, including this funny nose. Yeah, students were very happy, and they surprised me on Halloween's day with these costumes. Yeah, okay, so I don't know how much time I have. 1 minute, okay. So a famous novel in 10 seconds. Famous novel is a 4-color theorem. 4-color theorem says every map can be colored by 4 colors. This is a 4-color theorem, 4-color map of United States. 4-color theorem is a very famous one. Theorem, but it was a conjecture for more than 100 years. This is a map. We can connect a map to a graph. This is a graph model. It was a central problem for more than 100 years, from 18th century. It was proved. It was finally proved by Apple and Haken in 1976 by using computer. So I think using computer, because of the advances of technology, it's possible that many open questions might be able to be proved. These are my current students. Dorian sitting there, and my current Ming is there. They are funded by, my research is funded by National Science Foundation, and also related to, I'm also in part of NASA Direct STEM program, which I think probably you like. I encourage you to apply. You go to this Saturday workshop, and you get paid by attending this workshop, by learning very awesome things. Like in the past 1 month, we have people from Cornell University teaching us advanced Python. Student, you should apply. Community college student, we welcome you to apply. Professor Zhang has some flyers that, I know the font is too small, but she printed out some flyers, and you can check our website. Application is on our website. So welcome you to apply. So I think with that, I will. This is not a long story, but I want to tell you this breakthrough of a math conjecture. This conjecture was 50 years already, but the breakthrough was last year by a non-mathematician, de Grey, using computer to generate a graph more than 1,581 vertices. You know de Grey, he's a biologist. His bachelor's degree is computer science, and he self-taught himself biology, I think from his ex-wife. If you Google his name, you see his TED Talk for anti-aging. He's a CEO of a company. In the past 30 years, he's been working on anti-aging research. And on this paper, he thanked his professor who taught him graph theory 30 years ago. This is the very first breakthrough result in mathematics by a non-mathematician. This is the first time. And I think by advances of technology, it's possible that many beautiful conjectures might be solved earlier than we expected. And I think everyone, if you work hard, it's possible. Follow your passion, keep up your curiosity, and stay tuned. Thank you. I hope it's okay.
going to have present some.
Thank you. I'm Lauren Jacobs. I'm from the Office of Congresswoman Judy Chu. I really appreciated this today. I was a humanities major, but I did the Ashburner Lemma correctly, so maybe I'm changing my career now. So I just have a few certificates on behalf of the office and the Congresswoman. We really value PCC being in the district. The first one is for Dr. Robert Bell. He's here in spirit. Carrie Starbird. Dr. Brock Klein. Dr. Daphne Liu. Veronica Hamarillo. I butchered that, I'm sorry. Jared Ashcroft. Jorge Encinas. Yu Chung Cheng Hao. Appreciate it. And lastly, not least, the Pie Club. Okay. Thank you.